Hello and welcome back to Calculus 2, section 6.9, Exponential Models. So exponential models are present in every area of human endeavor, from population and biology to engineering to economics and banking to history, with carbon dating, environmental issues, medical field. So technically, every aspect of human involvement has exponential functions somewhere. And we're just going to highlight some of the use. I will say that the main equation is y equals a e to the kt, which is exponential model. And if you graph this way, this will be your a value. Time is on the x-axis because everything evolves in time. And this particular graph is for k larger than 0, which we call exponential growth. We usually model population. We look at the accumulation of money in the account due to compounding. We can take a look at the spread of the disease, right? Infectious disease like a flu or something. We can model the what else for exponential growth? The way the computer virus spreads through the network, that's also something that, or the rumors. So all of those exponential, they have exponential growth. And then if the graph looks like this, you will have k less than 0, which is the exponential decay, where we can talk about garbage decay, radioactive decay, so loss of mass, carbon dating for for history, historical facts, and so on. So there's a lot of that, and also metabolizing drug in the body. So there's a lot of application for exponential decay. Now all of the formulas look the same. I can write the population. So population in time is the initial population e to the kt. That's the population. Some of you worked on the amount is equal to the principal e to the rate times time. That's the money equation. Right? That's continuous compounding. The mass is equal to initial mass e to the kt. This is usually decay problems. Use this because the loss of mass. There's a half-life involved in this one. We'll take care of this one in particular. So I'll just say mass, but it's decay. Many other variations, the Newton's law of cooling, logistics model for population, and so on. It's just a lot of this stuff. Years of math ahead, you can find a lot of models that utilize same principle, a little bit different. So we can work on any example. So I would like to bring up real data to see. So what I'm going to do is I'm going to go to population clock website. So that's .gov, right? And This website shows US population 325 million and a half, and then the world population at 7.4 billion. And you can see how the population changes. Now this is the birth rate minus death rate. The death rate is obviously, I mean, no one is counting this real time. They are just these models for the data they get from death from wars and cancer and AIDS and everything else that is going on. Obviously old age, so all of that is there. Accidents. In United States, there are at least 30,000 accidents, just car accidents, 30,000 deaths a year, which would be greatly eliminated with the implementation of autonomous cars. But right now, 30 to 40,000 just in America die in car accidents. So all of those rates, death rates and birth rates, they're all taken into account, and this is the best model that we have. So to work on population, I'm going to say that now, which is year 2017, we are looking, so that's the T, we are looking at the population value of 7.4 billion people. Now I'm going to say over here, population world population. So world population in, let's say, 1980. 1987. 1980. It was 4.45. So 1980, 4.45 billion. So these are the two data points that we need to come up with the population model. Now this population model is going to be bad, obviously, on the long run, but it's going to be accurate on the short term to tell us certain. So let's see. I'm going to start by saying that year 1980 is set as t equals 0, which means that year 2017 is what? T equals 37. Good. So 37 years later. So you want to use the lowest possible year that you have in your data set and set that as the beginning of time, because at that point, when you have t0, you have p0, and p0 is 445. So, did I put the stream on? Okay, good. Whew. So now, I have the first step on getting the model where the population is the initial population. In our case, we are starting measuring from 1980. So that's 445 times e to the kt. Now k is the exponential growth rate. And now I can use the other data point. So use 2000, well, not 2017, now it's 37, comma 7.4 to compute k, the growth rate. So we have 7.4 is equal to 4.45 e to the 37k. So this is our calculation now for K. We use the calculator, and generally I ask you to calculate to 4 decimal significant figures on the decimal calculation, so you can shouldn't lose on precision right here. So 7.4 divided by 4.45 is 1.6629, and then you know that you are supposed to ln both sides to get rid of e. So you will take the ln of the value on the left and when I do the ln over here, I actually get 1/2, so 0.5086 is equal to 37K, and from there divided by 37, you get that the K is 0.013745, so 5. So there it is. This is our growth rate. And now I have a model. Population in time is going to be 445 e to the 0.01375 t. This is the population model that I have. Now, I can ask a question: when are we going to reach, let's say that one of the research said, or predictions said, that the carrying capacity of the planet is 15.2 billion. And some are as low as 10. The reason why they vary so much is because it depends on which standard you take to be the living conditions for the entire planet. We know it's varying. In Nepal, which is one of the poorest countries in the world, people live off of $1 a day, which covers whatever meals they have, and most of the people live like that. So in the United States, for $1 you get what?
Nothing.
Right, in terms of real food. So you can't even go to the vending machine for $1, right?
$1.25.
Yeah, so
Not dollar.
So the estimates for the carrying capacity of the planet are anywhere from 10 to 15 billion. But let's just say 15 billion, all right? So when? That's the question. Oh, first, let me just go. Is this a good long-term model? Long-term model. And the answer to that is hell no. Because the limit, time goes to infinity, of 4.45 e to the 0.01375 t is equal to infinity, telling us that you wait for a long time, there will be infinitely many people on the planet. No, they won't, right? So, no, it is not a good long term, but it's okay on a short term. You know, go back 20 years, go forward 30, 40, 50 years. The model is going to be fairly accurate. So it is good for, I don't know, plus minus 50 years, let's say. And then you're going to see some significant divergence from even that 50 years, maybe 40, I don't know. You can play with the model and see how well it fits the data.
To make it like a realistic model, you also have to add in the exact rate
Well, the number that I have is the population, and the current population is the number of people that are alive, which means the dead are already subtracted, right? So what I can do here now is I can ask when, meaning t equals question mark, when are we going to reach 15 billion population? Right? When? Well, the target is 15 billion. We have the mathematical model and we just solve for t. This is all pre-calc. There is nothing special. You will do the same calculation, divide by 445, ln both sides, divide by 0.03, and then the number you get, you have to add, right? Because we zeroed out at 1980, you will have to add that value. So use your calculators and calculate this. I'll do it on my own, and let's see how it all works out. $15 billion at this rate, 15 billion will reach in 50 years from today. 50 years from today. Yes?
How do you get 8? I got 8.837. What do I have to multiply it by to get that?
You probably typed something wrong, or maybe you forgot a 0 or something, because that's probably, looks like you factor 10 off. You just probably type 0.1. So 2068. You can go back in time, you can go forward in time when you have a mathematical model. Now, what are the questions you can ask? You can ask at what rate? You saw that briefly show up at the Google search that I showed. It says 10-year growth rate in percent. These values you can get them from derivatives, right? I can find of how fast the population is changing, how many people we add in 1 year by simply finding the derivative of our model and then just say, I don't know, put 40. That means in 2020, how many people will be added in 2020? It will show the change of population for 2020. So the derivative of our model in terms of time, so ddt, of 4.45 e to the 0.01375 t, when you find this derivative, that is going to give us the population, the equation that can calculate the change in population. So we have 4.45 times 0.01375. So it's going to be 0.01375 0.0611119 e to the 0.01375 t. So this equation over here can calculate change in population in any given year. So now the change in population for year 2020, well, that's t equals 40. So you will just plug 40 into this equation. So 0.06119 e to the 0.01375 times 40.
How do you get the 0.06119?
The derivative, the number in front of t drops and multiplies 445.
Oh yeah.
It's a chain rule, right? And it gives me 0.106 billion. So this means that 106 million people will be added worldwide in year 2020. You can calculate how many people lived and died from any year to any year, because you can integrate this equation, not derivative, but the original model. So if you want to know how many people we had since 1980 to, let's say, 2000, you will do integral 0 to 20, because it gives you accumulation, right? It sums up all of the values. So there's a lot of cool stuff that you can do with these models, as long as you understand. And this is what I said, as engineers, you need to understand what these things. You don't need to know how to compute integral or derivative, because machines do that for you today. But if you don't understand how to actually use this stuff to whatever is relevant to, then you're not good, because you can't do your job, right? So I gave you the population example, but then you might be a medical researcher, right? And I'm going to do the same problem now, except it's going to be a decay problem, and we can talk about Advil. We all know that the exponential model, once you do the exponential model, that decay model will never hit 0, which is the amount, right? In infinite time, it hits 0. So that means that every pill you ever took so far is still present to whatever minute speck is still in the system, right? Because the decay model never hits 0. This is the time 0 when you took the pill, and this over here is infinity where it's 0. And this is the t equals 100 when you die, right? So, you know, those are things to think about. So let's talk about Advil, let's say, that has the biological half-life 1.9 hours. And first of all, this Half-Life, apart from being an awesome video game, we also know that the half-life is the time in which half of the mass is lost. Now, I don't want to say decayed because we lose mass in different ways. It metabolizes, or it radiates out, alpha radiation or gamma radiation or whatever. So, you know, just important to know that half of the mass is lost. So when T equals lambda, mass equals initial mass divided by 2. So if I am to throw this marker away and it's going to rot forever, remember nothing ever goes for all the way. Maybe I have to wait 10,000 years to see half of it decay. I don't know exactly how much, but so if Advil has a half-life of 1.9 hours, I can actually calculate, I can actually find a mathematical model for Advil being metabolized in the body. I start from figuring out the decay rate. We know that the mass is equal to initial mass e to the kt. So now, when T equals lambda, mass is the half of initial mass. So we have this. And you see that mass doesn't matter. So we get that 1/2 is equal to E to the 1.9 K, and then you ln both sides and so on, so you are going to find a decay constant from here. So it is ln of 0.5 divided by 1.9, and we get the decay constant K, negative 0.3648. So now I have the mass to be the initial mass times e to the negative 0.3648 t. T is in hours. So now this is your mathematical model. You can integrate, you can differentiate. The limit in this case will tell you that in order to have the mass of the Advil to be completely gone from the system, you have to wait to infinity because the limit as t goes to infinity gives you 0. Anything else will give you a value. So yeah, it's going to be one molecule of Advil, but it's still going to be that one molecule there, right? So now, as you are looking into this equation, you can ask, well, how long do I have to wait to have, in hours, to have 90% gone, let's say. Let's say you want to, so how long in hours do we have to wait for 90% to be metabolized? Okay, so you want 90% gone of the original amount. So that's 0.9 m gone. Oh, sorry. So you want to have, do what? 0.1 left, yes. So if you want 90% gone, note that 1%, note that 10% is left. 90 and 10 is 100. M's will drop. And you just do again the ln both sides. It's just the same calculation over and over again. So ln 0.1 divided by negative 0.3648. $6.3 hours. You know how they say that you should take the next dose 4 to 6 hours, right? So if you're taking it 6 hours later, you still have 10% in your body. If you take it 4 hours, this basic calculation here shows that you have 75% gone and 25% left. The one that I did on the board. All right. One more problem. The decay has so many applications. Radioactive decay, garbage decay, the rate at which you eliminate technically anything can be. But I have my favorite problem that I always do when I teach pre-calc 1. So, did anyone heard of Doramad? Every student that I had in my class remembers this forever. Anyone? Doramad? Toothpaste? No? Who likes white teeth? No one? 2 people. Okay, fine. So Doramad was the first teeth whitening toothpaste ever made. 1940s. And it was based on a thorium isotope 229, which is a bit radioactive. Which they didn't know much about at that time, right? Just wonder of what stuff we use today, right? I can guarantee that like 200 years out over there, they were going like, yeah, those idiots used to drink milk. That's why they only live 100 years. Now we now live 500 years because we didn't drink the liquid from another animal. So, yeah, I know, right? It's not a human milk, it's a cow milk. It's for cows. I mean, I drink milk, but it's just a fun joke. That's why I'm going to die, along with all of you. On time, I hope. Yes.
There was a Boy Scout in 1995 that had like nuclear power. He stole like fire alarms from all around the houses and took out the little nuclear stuff and created in which police found out it was radioactive in our shed, in which it caused evacuation and cost like $10,000.
Where?
Down in like Minnesota or Ohio, I believe.
Cool. Well, yeah, there are sites. I mean, a lot of sites where the nuclear stuff happened. But Doramad was one of those interesting. They had their own campaign. Everyone had nice and white teeth, and then they died. So, well, it's safe to assume that it's 1940, 1943. So everyone's been dead since. So let's see some calculations. That's why we like math, right? What happened?
One of the pictures said radioactive cream.
Yeah, that was later. Because they had the campaign to sell it, and then they have to have a campaign to say, no, don't buy it anymore, right? Because that's, yeah. We're going to have to campaign for milk in 300 years from now. It's okay. So, thorium. 229 with a half-life. What's the half-life of thorium-229? I believe it's 7430. half-life of thorium-229, 7340. All right. So we are going to first compute K. So we know that half of the amount of toothpaste applied of thorium will be gone when we have the half-life of 7,340 years. M's drop. We ln both sides. So we get ln of 0.5 divided by 7,340 to get K negative 0.00009443. There we go. So now we have the model, exponential model, that we can use to compute stuff.
We want the entire decimal.
Well, you have to have 4 significant digits. The zeros are not significant, so you have to put as many decimals. Like if someone says use the 2 decimals, then 0.00, right? The problem turns to garbage. So we have to have a 4 non-zero decimals, 4 significant digits, right? All right, cool. So we are going to say today is I'm not sure what year they banned and stopped producing and banned the sale, but let's say it's 1943, right? And we have 2017 today. So 74 years since. So what am I looking for? What percent is left? So I'm going to call that lowercase p times capital M, right? So percent times the original amount equals the original amount e to the negative 0.00009443, and then times 74 years. M's drop, and we have that the percent is equal to this calculation. Now it's a very easy calculation. So I have e raised to the answer, I'm sorry, open parenthesis, answer times 74, and I get 0.993%. Sorry, not percent. 99.3% left. These are the most beautiful corpses you have. All have white teeth. 0.7% is gone. 99.3% of thorium deposits which make the teeth glow white are still there. Right? 70-year for. How long do you have to wait for half of the thorium to be gone? How long exactly? 7,340 years exactly. If you were expecting to see any other percent other than something insignificant gone, I mean, you have to understand, half-life says this is how long you have to wait for half to be gone. So this answer, waiting 74 years, where you have 7,340 for half, for 50% to be gone, right? It makes sense. to have 99.3% left after 74 years. So yeah, it's one of my favorite decay problems. What else do you have? You have carbon dating. I watched a documentary on some art that was found. I did carbon dating on art, pieces of art that was found. All of the art from the past had the paint made out of flowers and plants, organic material, so carbon C14 is present, and you do the carbon dating on that. We know the half-life. We know half-life for every element, so you can do the carbon dating for technically anything. You can't carbon date pyramids, right? Because they're made out of stone. You can dig around the pyramids and hopefully find some fire pits and graves and pots and stuff that was made out of organic materials, and you carbon date those, and then you hope that those were there at the same time when the pyramids are built. But you can't carbon date the pyramid. And also, if you find the content in the pyramid that it's organic in nature, you can try. So yeah, if there is a mummy, you can pretty much pinpoint a year because of the carbon dating, right? But that mummy could have been placed there 3,000 years later, you know, or it could be placed as soon as it was finished. So, you know, there are limitations to those. But if you find an old scroll, that's going to be made out of the tree eventually, and you can carbon date that piece. So that's something that you have to be mindful of. How do you do carbon dating? Here is the problem. You have the half-life for C14. You say, okay, 70% C14 left, carbon isotope 14, right? So you just look and you do the same calculation that P, right, would be the value of 70% left, and you just do the calculation from there. So all of the problems are the same as in pre-calculus. And what we are focusing on here is kind of pushing the story forward in terms of, I can take the derivative for this and say that when we wait to infinity, all of the thorium will be done and gone. I can take, so that was the limit as time goes to infinity. I can take the derivative and find the rate at which we are losing mass, the rate at which we are making money, gaining population. Decay of garbage. So I believe 5 years ago, I challenged my math club to figure out mathematics of decay of this marker. That's how I know that this marker is actually 16.2 grams, because they went to the chemistry lab and used those precise scales to measure the weight. So these markers are 16.2 grams. Then they researched the plastic to find the half-life. And once you have that, as soon as you have the half-life of the plastic out of which it's made, you can find the equation. And then from there, you can calculate. And I believe it was along to lose a significant amount of this marker. I believe it was 5 years ago. I think 16,000 years or something like that. Those shopping bags, like, you know, go grocery shopping or something, each one of those bags, 10,000 years to decompose. So there's a lot of stuff that you can compute with these. As I said, you've seen the medical field, you see the radioactive, right? When can people go back and live around Chernobyl, and you know, things like that. So a lot of cool stuff to be computed, as long as you know that you can take the limit to check the validity and sanity of your formulas, make sure that they make sense to some extent. Then you have the derivatives that will give you the rates of change at any particular moment. And then you also have the integral that will calculate the accumulation of population, money, or whatever else. So that would be this section. All of the problems are basically 99% your pre-calc stuff that you already seen before, and then try to practice the important part, which is the calculus component, what limits, derivatives, and integrals as well, to see what those can bring. So we'll take a 3-minute break or so, and then we are going to dive into hyperbolic functions, which we will have to finish next class. We have 2 sections to go.